So, good evening, everybody. Good evening. Yes, this is the end of everything. You can see from the subtitle, I'm going to be talking about the fate of the Earth and the Sun and the galaxy, and ultimately the fate of the universe. So we're not going to jump straight to eternity. We're going to take it chronologically, bit by bit. And perhaps a preferred subtitle might be something like that. We're not going to jump all the way there. I'm going to take it a little bit at a time. So I'm going to introduce, firstly, where the universe came from before we start thinking about the ultimate fate of what's going to happen in the future. And then we're going to talk about what's going to happen to the Earth, the Sun, and the solar system. And then we'll think further ahead in time and think about what's going to happen to stars and galaxies. And then we'll jump to the far, 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 far future and talk about what is the ultimate fate of the universe. Let me just get the cursor out of the way. Okay. And then I'll finish with a little wrap-up at the end. So firstly, let's just make sure we know where it comes from. Rather than starting absolutely from now, let's just remind us what happened 13.8 billion years ago, a different talk. You can see why I've called this one the end of everything, because it's a bookend to the original talk on the beginning of everything. So in the original talk, I say that what we now see as the observable universe, something like 100 billion light years across, everything in that volume used to be a lot closer together. We know the universe is expanding, so if we run the clock backwards, we deduce that everything that we now see in the observable universe used to be a lot closer. In fact, it used to be in a volume approximately the size of a golf ball. That was a long, long, long time ago, and since then the universe has expanded and various things have come to be. For instance, protons and neutrons, which make hydrogen and helium. So basically, in 3 minutes, the universe was made. Okay, there's a few details to be sorted out after 3 minutes, but effectively it took 3 minutes to make all of the hydrogen and helium, which then gives us everything we see, the stars, the planets, the galaxies, etc. And as I indicate here, once we've got hydrogen, we then understand everything, such as galaxies, stars, planets, mountains, trees, snowflakes, rainbows, cats, etc. Well, maybe not cats, because I don't think anybody really understands cats, but once we've got hydrogen, we know where everything else comes from. So we're going to take it as read that we've got a universe full of hydrogen, helium, and apparently some stars and galaxies, and we're going to ask what's going to happen in the future. In order to keep track of where we are, I'm going to use this timeline along the top and indicate where we are on this timeline. Each number here represents 10 times further into the future, because we can't possibly do it on a linear time scale, otherwise it doesn't really make sense. So we're talking about now being on the left, and we're talking about, well, I won't actually be talking about 10 years and 100 years, but I'll be starting at around 1,000 years from now. So 10 to the power 3, 1,000 years, and then we'll be ratcheting up 10 to the 4, 10 to the 5, 10 to the 6, 1 million years into the future, 10 to the 7, 10 to the 8, 10 to the 9, a billion years into the future, and then, of course, up to 1 trillion years into the future. Okay, that's not quite eternity, but that will do to start with. And so this little red square will tell us where we're on this particular timeline. So I'm hoping that you're all either familiar with the idea of 10 to the power n being an indication of time. If not, just treat this as a scale that tells us where we are. So before I forget, let me acknowledge the fact that there was a paper written by these two gentlemen in the Reviews of Modern Physics, in which they've tried to calculate when certain astrophysical events might take place. And I've used that to try and get the chronology of the slides in the right order. So we're going in time order, not necessarily in what's happening to the Earth, what's happening to the galaxy. We are simply moving forward in time. So I'm going to assume that mankind is not going to exterminate itself. I'm going to assume that we are going to get climate change under control, and we are not going to basically annihilate ourselves in the next 10 or 100 years. So I'm starting with what's going to happen when we move 1,000 years into the future. And one thing that we do know, that we can calculate quite accurately, is that the rotation of the Earth is slowing down. Again, a different talk, talking about how the tides raised by the moon are slowing the Earth down. At the moment, because the Earth is slowing down, we add a leap second every few years to try and keep our clocks in sync. In 1,000 years' time, the Earth would have slowed enough that we'll need to add leap seconds, not every few years, but we'll have to add a leap second every few weeks to keep our clocks synchronized. In other words, our clocks synchronized with the rotation of the Earth. So that's possibly the first thing that we will notice. If we think about what's going on in the environment around us, it might be that some stars go supernova, but of course we can't actually work out when that's going to be. We can say the likelihood of a supernova occurring, we can estimate the time period over where we might expect to see a supernova of unstable stars that seem to be coming towards the end of their lives, but of course we can't pinpoint when it's actually going to be. Conversely, when we think about what's happening with the Earth, we can make some fairly solid predictions. So for instance, we know about the spin of the Earth. At the moment, the Earth's axis is pointing close to the North Pole, the star that we call the North Star, Polaris. But we know that over a time period of 26,000 years, the Earth's axis will precess and will make a little circle on the sky. That's something that we know fairly accurately, so we can predict with a great deal of precision that although the Earth's axis is currently pointing at Polaris, we know that in, roughly speaking, half of 26,000 years, something of order 10 to 12,000 years from now, the North Star won't be Polaris, the North Star will be over here somewhere, and it will be very close to Vega. So a lot of misconceptions, perhaps you know that a lot of people seem to think that the brightest star in the sky is the North Star. Where they get that from, I don't know. But in 10,000 years, it will probably be true, because Vega will indeed be the North Star. What are the consequences of the fact that the Earth's axis is going to be rotating and then pointing into a different part of the sky? Well, one of the consequences is the fact that at the moment, with the Earth's axis pointing at Polaris, because the Earth's orbit is elliptical, it just so happens that at the moment we are closer to the Sun, perihelion, during northern winter. In other words, we're closer to the Sun where in principle we would get more heat, but because the Earth's tilt is tilting the northern hemisphere away from the Sun, that means our summers aren't too drastic and our winters aren't too cold. But in 10,000 years, when the Earth's spin is pointing the other way at Vega, that means we'll be nearer to the Sun in perihelion during the summer. In other words, they will exacerbate each other. We'll be not only tilted towards the Sun, but we will be physically closer to the Sun as well. So the seasons will become more exaggerated, if you like, in a few thousand years, simply because of that. So regardless of the fact that we are trying to mitigate climate change by not having any man-made influence, we must remember that over periods of tens of thousands of years, there will be changes to the climate, regardless of what we do, simply because of the nature of the Earth's spin and the Earth's orbit. And long-term variations in the Earth's climate that are due to the spin of the Earth or the orbit of the Earth are called Milankovitch cycles, if you want to go and look that up another day to find out more about how these things work. We've now moved, you may have noticed, onto 10 to the 5. So now we're not talking about tens of thousands of years into the future, but perhaps closer to 100,000 years into the future. You know that we've launched probes into the solar system. For instance, in the 1970s, we launched Voyager 1 and Voyager 2 to go past Jupiter, Saturn, and then Uranus, Neptune, and then leave the solar system. Well, Voyager 1 started to leave after Saturn. Voyager 2 went on and then started to wend its way through interstellar space. We calculate from the direction that we know they're going. We know very accurately which way they're heading, and we know fairly accurately how fast they're going, so we can work out what Voyager 1 and Voyager 2 are going to be doing. And it just so happens that Voyager 1 in the top left there, before long, on a timescale of order 10 to the 5 years, maybe 40 or 50,000 years or so, Voyager 1 is going to go past the star called Gliese 445. And Voyager 2, down at the bottom of the picture here, that's going to go past the star called Ross 248. So we know that these two emissaries are going to pass nearby stars after a time period of order tens of thousands of years. Pioneer 10 and 11 were actually launched earlier than the Voyagers, but they're not actually traveling as fast, so the Voyagers are going to get there first. Pioneer 10 is actually heading off in the direction of Aldebaran, and Pioneer 11 is actually heading off in the direction of the center of the galaxy. We'll say a little more about Voyagers a little bit later. Again, on this timescale of order 100,000 years, we realize that ice ages come and go on that sort of period. In other words, when we look at the historical record, we see that ice ages are periodic. Not strictly periodic, but they certainly come and go. And the period is of order 100,000 years or so. And we know that currently Earth is not in an ice age. It's in this so-called interglacial, or this little warm period in between ice ages. We entered this stage fairly recently, so it's likely that the next ice age is going to come along in about 100,000 years or so. That's another manifestation of changes to the Earth's orbit, which is part of these so-called Milankovitch cycles. If you look back at when things were particularly drastic in terms of the cooling effect on the Earth because of changes to the Earth's orbit and the Earth's spin, there was a time when the Earth was entirely encased in ice, not just an ice age which expands the ice packs at the North and South Pole, but basically the entire planet was covered in ice, so-called snowball Earth, quite a long time ago. Coming back to the rotation of the Earth, I said the rotation of the Earth is slowing down because of the tidal effects of the Moon. The fact that the Moon raises tides on the Earth means that the Moon is effectively stealing angular momentum from the Earth and using it for itself. Now that we've gone a little bit further into the future, this is now 100,000 years, we find that leap seconds, far from being added every few years or every few weeks, we would now need to add an extra second to the day every day. In other words, the rotation of the Earth, the period is now not 24 hours, but 24 hours and a second. So we would have to permanently have an extra second in every day, rather than just add one as and when we need it, according to our calculations of the Earth's rotation. I said that we can't predict when supernovae are going to be, when they're actually going to occur. This, in the southern hemisphere, Eta Carinae, looks like a very good candidate. When we look at it, with this picture from the Hubble Space Telescope, for instance, we see that already it started shedding some of its outer envelope of gas. In other words, it looks like it's rather unstable. It seems to be producing shells of gas that have been coming off for thousands of years, and it does look like it's on the verge of going into a supernova phase. We can't be absolutely sure. We can't predict when, but it has been stated that on a timescale of order 100,000 years, it's thought that Eta Carinae could well go into its supernova phase. A similar thought is carried on with Betelgeuse, but of course, again, we can't tell. Remember, we had a little bit of a scare when Betelgeuse changed its brightness, and people were saying, is this the first sign of something happening in the outer atmosphere of Betelgeuse? Well, possibly, but again, we think that maybe it's due on the scale of 100,000 years. We'd be very lucky if it went off during our lifetime, so it's much more likely to be sometime in the distant future. This is a genuine picture of the Orion constellation, but photoshopped on the top is what Betelgeuse might look like if its brightness was what we expect to be for a star that's, whatever it is, 600 or so light years away. It would be spectacular and probably visible during the day, but it makes a real mess of Orion. Given that it's such a beautiful constellation, it'll be a bit of a shame for it to lose one of its signature stars. But that rather nice picture was taken in Prague with the snow and then photoshopped to show the effect of what might Betelgeuse might look like. But some supernovae are worse than others in the sense that there is a star not so far away, Wolf-Rayet 104. This is a particular star. It seems like it's so far away it can't possibly be a problem for us. It's 7,000 light years, and that sounds so far away. That's much further away than Betelgeuse. So surely if Betelgeuse going supernova isn't a problem, surely this thing is not going to be an issue. Well, the problem is the fact that we have these jets, and its death may result in a radiation burst more serious, as far as we're concerned, more powerful than a supernova, because the rapid rotation of this system is producing jets, very energetic jets. And the question is, are we in line with one of these jets? If the jets miss us, then we're safe. If these jets happen to be pointing in our direction when it happens to go supernova, then a huge amount of radiation is going to come our way. It's very difficult to tell exactly what that direction is, so it is being watched. And it is thought that there's a small percentage possibility, perhaps a few percent, that these jets are actually pointing in our direction. So it might take a while, again, perhaps 100,000 years or so, for this thing to actually die, but the possibility is that when it does so, despite its distance, it might be a problem for us. If we are in the direct line of sight, it is calculated that it could even evaporate the biosphere. In other words, it could remove the Earth's atmosphere and boil the oceans. There's that much energy in these jets, but of course we'd have to be perfectly lined up for that to be the case. So it's something we need to keep an eye on, as well as Betelgeuse, as well as Eta Carinae, as well as Antares, which could all go supernova. We have to watch these objects as well. More distant, but possibly even more deadly. On a similar timescale, we're just nudging into a little bit further ahead, perhaps 1 million years or so. A star is going to come close to us. That doesn't mean that the two stars are attracting each other as such. It means all the stars are going around the Milky Way over a time period of one rotation in perhaps a few 100 million years or so. And as different stars go around the Milky Way, some of them get a little bit closer and then get further apart. And this is a representation of our sun in the middle there with an Oort cloud of lots of icy particles at a huge distance from our sun. And it's thought that a star called Gliese 710 is going to come close to us and then recede from us. It's not actually doing that, it's just an artifact of the way we're both going around the Milky Way. But if you get a large object like a star that comes into the Oort cloud, it's going to be a huge disruption to the Oort cloud. So at this particular point, perhaps about 1 million years from now, we can expect to get loads of asteroids and comets coming into the inner solar system. It's been calculated that we might get some spectacular comets, 1 a month, for 1 million years. In other words, it's going to be a very disruptive occurrence. And if you're going to think about setting up a camera, waiting for this, because it's going to be spectacular, bear in mind that for a short time, our solar system will actually have 2 stars in it. It'll have 2 suns. So there's a photo opportunity for those of you who think that you want a sort of Tatooine-type picture. Similarly, we're still on a time scale of about 1 million years or so, and here's a picture of Meteor Crater. Not because we're expecting an impact like this every 1 million years or so. We would expect impacts like this probably more often than once every 1 million years. On looking at that, we do ask ourselves, wasn't it lucky that it happened to hit just next to the visitor center, but it missed the visitor center by a whisker? So that was lucky. This is not saying that we would expect one of these every 1 million years. What we're saying is that in 1 million years, we would expect erosion, weathering, to actually start to reduce the appearance of this. So this might be tens of thousands of years old, but in 1 million years, we would expect normal weathering, heat and cold, and the effects of water and freezing, etc., will start to erode the appearance of a crater. So we might not be able to see Meteor Crater in 1 million years' time, for instance. And you might say, well, that's the property of Earth, but surely that's not the case of other bodies. For instance, footsteps on the moon are going to last forever, aren't they? Well, no, because there isn't weathering as such, but there is erosion. Because the moon is bombarded with micrometeorites, I mean, that's effectively what produces the fine regolith that we're seeing there. It's basically rock that's been pummeled for 1 billion years by lots of micrometeorites. So the footsteps on the moon will not last forever. Micrometeorites will eventually erode the signs of the lunar landings. And it's been estimated that even the hardware, even the lunar lander, etc., and other hardware that's been left there will eventually erode and decay because of the effect of micrometeorites. So we are often told that the footsteps will be there for ages, but perhaps the footsteps might only be there 1 million years. I mean, that's not a bad legacy, but it'll only be 1 million years or so. I said earlier that we've sent probes out. I mentioned Voyager, and of course Pioneers have gone as well. And slapped to the side of the Pioneers was a plaque, courtesy of Carl Sagan, telling extraterrestrial civilizations where we came from, basically telling them essentially who we are, or at least how big we were, and the little diagram on the left tells the aliens where we are in the galaxy, effectively. So Pioneer is expected to go past the star just like Voyager is on a timescale of tens of thousands of years. But this is 10 to the 7. This is 10 million years into the future. What's going to happen is probably that plaque will start to get rather eroded. You think of this thing flying through space, and space is empty, so why would the plaque ever change? Well, no, space isn't empty. There's always something out there. Even in the interstellar medium, there is a medium. There is stuff there. There is small particles. There are molecules. And if you're traveling for millions of years, eventually that plaque will get eroded. So when Pioneer passes the nearest star or the next star or the next star, any aliens that pick it up will be able to read the plaque. But if we wait for a few million years and somebody picks up Pioneer, Pioneer is going to be in a really grotty state, and probably the plaque will be unreadable. So at that point, the aliens will not be able to tell where Pioneer came from. We're now going to 10 to the 8. We're now 100 million years into the future, and Saturn's rings are going to change. But before we say that, let's just think about how Saturn's rings came to be. One argument is perhaps something like the moon Mimas made Saturn's rings. And you look at Mimas and you might think to yourself,
that's no moon, it's a space station.
Because there is a certain similarity there, but a simulation has been done to try and find out what would happen if we take a moon a bit like Mimas and smash it to smithereens, for instance with the impact from a comet. What would we expect to get? And you notice that it doesn't actually take that long for the debris of a moon to actually spread itself around the entire planet. So in other words, it's possible that Saturn got its rings a matter of days or months after a particular moon got pulverized, perhaps with a collision with either another moon or with a comet or something like that. And all of the debris that's in Saturn's rings that would be generated very quickly would start to drift inwards. And over millions of years, all of that debris would form the rings that we see today. That's the current Hubble Space Telescope picture of the rings. And that inward migration is still happening. So the rings might be millions of years old, but in 100 million years' time, essentially all of the ring material will have migrated inwards, and basically Saturn's rings will be no more. So if you like planetary imaging, get going now, because you've only got 100 million years before you're no longer going to be able to do that. So it's a shame to think that the beautiful aspects of the solar system that we take for granted won't always be there. And generally speaking, when we think about the solar system, it's very tempting to say, well, the solar system works according to, well, it's basically just a big orrery, isn't it? It's clockwork, and whether we have an orrery or whether we have a tellurian, it's very tempting to think that it is just clockwork. You put the numbers in Stellarium, you see where the planets are going to be tomorrow or in 1,000 years' time, or you dial backwards and you find out what did the sky look like when Christ was born or in the age of the pyramids. You almost take it for granted the fact that Jupiter has a particular orbit and we know where it is now, so we will know where it is in the future and we will be able to calculate where it was in the past. But that's only true up to a point. When we're thinking about timescales of 10 to the 8, 100 million years or so, the solar system is actually chaotic. It is not clockwork. We cannot tell where Saturn is going to be. We cannot tell where Jupiter is going to be. We cannot tell where the Earth will be in its orbit on this timescale. Too many things could change. You may be used to the idea that people have tried to simulate what the early solar system looked like, the fact that planets have swapped positions, etc. Well, similarly, we cannot tell what the future is going to be. On a scale of a few million years, perhaps we've got a good idea. But on a scale of 100 million years, the solar system is chaotic, and hence we cannot tell what things are going to look like. We can't even tell what the order of planets is going to be on this sort of timescale. Thinking a bit further afield, beyond the solar system itself, this is a little schematic of the Milky Way. That's where we are. And at the moment, we're sitting on a little spur in between two fairly dense spiral arms of the Milky Way. The entire Milky Way is rotating on a timescale of about 10 to the 8 years or so. And on that sort of timescale, we are going to migrate from a relatively sparse area in between two spiral arms. We are going to drift into one of the spiral arms. In other words, we're going to have a lot more neighbors in 100 million years or so. Why should it matter as to how many stellar neighbors we have? Well, think about Gliese 710 that happens to come in and disturb the Oort cloud. If we've got lots of stellar neighbors, that's going to happen far more often. And so on this sort of timescale, what's going to happen is probably we're going to get another one of these. In other words, we're going to get an asteroid or a comet coming our way, and we know that's happened in the past because we've seen extinctions as a function of time that have quite definite spikes in them. These are the ones that effectively define the various eras. If you remember the most recent spike where there were a lot of animals made extinct, That's the so-called KT boundary. That's the classic one that killed all the dinosaurs. We survived, but many, many, many species were completely wiped out at the time. We know that has happened in the past because we can see it happens quite a few times over a period of a few 100 million years. And on this time scale, we are fairly sure it's going to happen again, simply because we're going to move into a much more highly populated area of the Milky Way. We're going to have lots of neighbors. We're almost certainly going to have lots of asteroids and comets coming our way. Sooner or later, one of them is going to hit, and we're going to have an extinction level event. So obviously an artist's impression, but it might look something like this. A huge chunk of rock. You can see on the left-hand side there, it seems to be heading directly for Italy. That's their problem. Okay, bad news for Italy, but probably, let's face it, the rest of the world as well. Anything on that sort of size is going to be an extinction level event and will take out a large fraction of the species on Earth. Species will quite definitely be exterminated. The only real question is, will one of the species be us, or will we find a way of getting around that? Coming back to the idea of having lots of stellar neighbors, if we've got a lot of stars in our neighborhood, some of them, sooner or later, are going to go supernova. So instead of worrying about a supernova like Betelgeuse 600 light years away, or Wolf-Rayet stars 7,000 light years away, we're going to have to worry about the fact that we might have a supernova within, for instance, 100 light years or so. Within 100 light years, a supernova would be a problem for Earth. It wouldn't necessarily be an extinction level event, but it would produce a huge amount of radiation. If there was a supernova 20 light years away from Earth, that would be bad. That would probably sterilize the planet. That would probably remove the atmosphere, remove the oceans, and sterilize every living organism on the Earth. So we certainly don't want any neighbors at that sort of distance that are coming towards the end of their lives and possibly going supernova. It's not necessarily likely, but it will be more likely when we move into one of the denser arms of the Milky Way. We can't tell when that's going to happen. We can't say with any certainty we will be incinerated by a supernova at any given time. But we know there have been supernovas not that far away from us in the past. We can tell that because supernova, approximately, it's been calculated that a supernova within about 100 light years is likely to leave a particular isotope called iron-60, and it could easily dump that into the Earth's sediments. Now, why is that meaningful? Well, because we know that iron-60 is radioactive, and iron-60, after a few million years, will change into something else. It actually changes into cobalt, which then changes into nickel. But the point is, iron-60 is not stable. It will change. Therefore, if you find some iron-60 in the Earth, and indeed people have looked and found iron-60 in the Earth, you know that it changes on a time scale of a few million years. So if you find it, that means it's been dumped on Earth within the last few million or perhaps tens of millions of years. So we know that there have been supernova not that far away that have been close enough to dump that particular isotope in Earth. And it's impossible to tell the exact timing, but it could well correlate with some of the extinction level events that we've seen in the past. So we know it has been a problem, and it's quite likely that it will be a problem on this sort of time scale of perhaps tens to hundreds of millions of years. I keep coming back to this idea that the Earth is slowing down. If we're talking about this many years into the future, the Earth will have slowed down considerably, because for the last 100 million years, the moon has been raising tides on the Earth and slowing the Earth down compared to its current day of 24 hours. At this point, 100 million years, the length of the day is now 25 hours. So it's ridiculous to start asking about adding leap seconds to try and keep things in synchronization. Leap seconds are completely out of the window. At this point, we may well have decided just not to have a 24-hour clock at all. It might be that we've gone decimal by then, and we have a 10-hour day or a 100-hour day, or we just have a number of seconds in the day, and to hell with hours. So on the current time scale of thinking about the Earth's 24 hours, the Earth will have slowed down to a day of about 25 hours by this point, and the moon will continue to have got further away from the Earth. The distance is currently increasing at a rate of a few centimeters a year or so, and over that sort of period, the moon will end up getting so far away, it will actually be impossible to have total eclipses. So at the moment, we're lucky enough to be in a position where the disk of the moon is close enough that the disk can occasionally cover the sun. The actual distance to the moon is changing because the moon's orbit is elliptical, and the sun disk changes slightly because the orbit of the Earth around the sun is elliptical as well. But there are times where the moon can cover the sun, so we can get a total eclipse. Once the moon has traveled further away, once we have a moon orbit that's significantly larger by 20% or so, then it will be impossible for the moon to completely cover the sun. In other words, total eclipses of the sun will never take place again beyond this sort of time period. We're now talking about more than 100 million years. We're now talking about something close to 1 billion years. So the Earth will continue to slow, the moon will continue to get further away, and then we'll have to put up with annular eclipses basically until the Earth is destroyed, whenever that may be. The moon stabilizes the tilt of the Earth. So as well as not having eclipses, which is a bit of a shame for astrophotographers, rather more importantly perhaps is the fact that having the moon relatively close to us tends to stabilize the obliquity, the amount of tilt of the Earth relative to the ecliptic. When we look at historical records, we think that the tilt of the Earth hasn't changed by more than about a degree either side of its current value of 23.5 degrees. In other words, if we look at this little cartoon on the left, you can see it's rocking slightly. That's the total amount that the Earth's axis has changed in terms of its tilt relative to the ecliptic. Hardly anything. A degree in 23 degrees is not much. In other words, it doesn't really change the equator, the tropics, or the poles. But if you take the moon further away from the Earth, it doesn't have the stabilizing effect that the moon would have if it was close. If you remove the moon, the Earth's axis is free to flop around how it likes, and we won't have an axis that's tilted at 23.5 degrees. It will go all over the place and could vary very erratically, thus causing us real problems in terms of climate. Again, the climate could change very dramatically because of that. I said very early on that Voyager left the solar system and is heading on to stars on a scale of tens of thousands of years or so. Why have we got this at 1 billion? Well, we think that's the point at which it will no longer be possible to read the record. Note that this is longer than Pioneer. The Pioneer plaque will be eroded long before now. But the Voyager record that's being sent so that civilizations can listen to our greetings and our music, etc., that disk, that record, is actually behind a cover. And that cover is going to get pitted and eroded, but it's thought that the disk itself might last for 1 billion years. So it's going to take thousands of years to pass the first star, and then a few thousand years to pass the next one, and a few thousand. So within that first 1 billion years, there are plenty of opportunities for other civilizations to pick up the record and start listening to it and start saying hello to Earth. It might be a problem after 1 billion years, not because the record is unplayable, but because the instructions are on the cover. And if the instructions on the cover get eroded such that you can't read the instructions, you'd have to rely on the intelligence of the civilization that picks it up to figure out how to get the information off the disk. But perhaps it's still possible. So there could be many, 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 many civilizations in principle on Voyager's route that are potentially capable of picking this up because it is so long-lived. Of order, it's only an estimate, but it's of order 1 billion years or so. Now that we're talking about 1 billion years rather than just millions of years, we're getting to the point where the sun, before too long, is going to start running out of hydrogen. It's about 5 billion years old. It's going to be probably 5 billion years before it goes into its red giant phase. But on that sort of time scale, its luminosity is going to start slowly rising, perhaps 10% per billion years or something. So the sun's luminosity is going to creep up year after year after year. And that is going to drive the Earth into a greenhouse effect. So it's going to take time. It's not going to become a red giant in 1 billion years, but over the next few billion years, it will start to move towards its red giant phase. and it's calculated that the greenhouse effect on the Earth could push the surface up to a fairly warm 80 Celsius or so. Whether or not we can survive that, you could say, no problem, we just go underground or put more sun cream on or something, but it is obviously going to be a problem for mankind trying to exist on a world where the average temperature is getting close to the boiling point of water. The sun is going to expand as it becomes a red giant, and it has been said many times that the sun will expand and engulf the Earth. And if we think about the surface of a red giant and think about the Earth, well, we can imagine that might be a problem. If the sun's surface is effectively going to expand to the point where it's either engulfing or almost engulfing the Earth, how can we possibly survive that? One thing that is sometimes overlooked is that the Earth won't necessarily get engulfed by the sun. It's often been said that the sun as a red giant is going to expand to the point where it's about the size of the Earth's orbit. That is possibly true. But one thing that must be borne in mind is that as the sun goes into its red giant phase, the solar winds become very strong, which is effectively removing mass from the surface of the sun. The sun's mass will decrease as it goes into its red giant phase. And if the sun loses mass, that means there's less gravity pulling on the Earth, which means the Earth's orbit actually gets larger. So in this little cartoon on the left, which is not to scale, you can imagine the sun is getting larger, but as it does so, it loses mass, so the Earth actually moves out to a larger radius. So yes, the sun will engulf the Earth's orbit as it stands at the moment, but that doesn't necessarily mean it will engulf the Earth. Perhaps the Earth will move to the point where it's so far away from the surface of the sun, it might conceivably survive. Whether we survive or not is a different matter, but the Earth as a planet might survive the sun going through its red giant phase. As the sun becomes a red giant, it produces a very large envelope of very tenuous gas, which eventually gets blown off into the interstellar medium to form a planetary nebula. And what's left behind is the core of the sun, effectively, which is a very hot object, which we call a white dwarf. There's no longer any nuclear reactions going on at the core. It's just hot because it used to be the core of a star undergoing nuclear fusion. So the white dwarf will eventually cool down, but it starts off as a very hot object, many tens of thousands of Kelvin. Having hydrogen converted into helium for most of the sun's life, and then towards the end of its life, having helium converted into probably carbon, maybe nitrogen, oxygen, etc., we probably end up with a white dwarf, which is essentially carbon. And it's been hypothesized that if you have something the size of the Earth that's made of carbon, might it be a diamond? It's going to be interesting to try and calculate whether or not the pressures and temperatures are right to actually form the carbon of a white dwarf into essentially a diamond the size of the Earth. An interesting idea. If the Earth survives, if the sun blows up to a red giant and doesn't completely destroy the Earth and blows off the outer atmosphere to the interstellar medium, we're left with a planet which currently has a magnetic field, but the Earth's core is cooling, and it has been for billions of years. It's nothing to do with the fact of how much radiation it gets from the sun. The Earth's core at the moment is molten, not because of any external temperature, but because of radioactive decay in the Earth's core. Eventually, the Earth's core will cool down. And it's been calculated that on this sort of scale, the same sort of scale as it would take the sun to go through its red giant phase, it is thought that the Earth's core will cool and perhaps solidify. At the moment, we have a magnetic field because we have a molten core and a dynamo. If the Earth's core solidifies, like Mars is thought to have done, then we lose the magnetic field, in which case we're then exposed to radiation. Perhaps not so much from the sun, but certainly radiation from cosmic sources. So if we survive the sun going red giant, we then get pummeled with radiation, which is bad news all round. Almost just to put icing on the cake and to say, well, the Earth might survive the sun going through red giant, and it might survive losing its magnetic field. At about the same time, we're going to collide with the Andromeda Galaxy. So the Andromeda Galaxy is getting close. That's what it might look like in sort of 3 to 4 billion years or so. The Andromeda Galaxy will start to get very large. We're not sure if it's going to be a head-on collision or a glancing blow. We can't be absolutely sure at the moment. but what is fairly certain is that the two galaxies are going to pass through each other. So in this particular picture, we can distinctly see Andromeda on the left and the Milky Way, which pretty much looks the same as Andromeda, but of course we're looking at it from the inside. So two spiral galaxies will hit each other, and in 3.8, 3.9 billion years or so, the two spiral galaxies are going to pass through each other. And there's going to be an absolute riot of new star formation. It's unlikely that stars are going to collide with each other, but certainly all the gas in one galaxy is going to collide with the gas in the other galaxy, and there's going to be so much turbulence, we're going to have a new star-forming region, a whole new star-forming phase of the two galaxies. They will probably pass through each other, and temporarily we will see Andromeda coming out the other side, probably taking loads of other stars with it as well. So we won't be able to say this star definitely came from the Milky Way and this star definitely came from Andromeda. They will lose that identity. And after a little bit of toing and froing, they will effectively merge together into one mega galaxy, which I guess we'll probably have to call not Milky Way or Andromeda. We'll probably have to call it Milkdromeda or something. But we've got plenty of time to think of a name, so that's okay. We've got a few billion years to worry about that. After 5 billion years, we'll have two nuclei with two supermassive black holes, but even the supermassive black holes eventually will merge together into one larger black hole at the core. I've been talking about how the Earth is slowing down and the Moon is moving away. This, by the way, is a picture, not a Photoshop. That's a genuine picture of the Earth and the Moon taken from a long way off. So it looks like it sort of doesn't belong there. It looks like this doesn't belong, and it looks like it's just a sort of a schematic to show you the relative size. But this is the far side of the Moon. That's why you don't recognize it as such, because it's the far side taken from, I'm not sure how many millions of miles away. But if you go to this far in the future, the tidal effects of the Moon on the Earth have resulted in total locking of the two together. In other words, one day is the same as 1 month. The length of time it takes the Earth to rotate once, i.e. a day, is the same as the length of time it takes the Moon to go around the Earth, i.e. a month. So not only does the same face of the Moon always face the Earth, which it does at the moment, the opposite will be true. The same face of the Earth will always face the Moon. The Earth will be tidally locked to the Moon, just like at the moment the Moon is tidally locked to the Earth. So what you can say is that there will be there will be points on the Earth that always have the Moon in the sky. In other words, the Moon will not move in the sky. The Moon will always be in the same place. Certain places on Earth will always see the Moon, and there will be certain places on Earth that will never see the Moon. The Moon will never get above their horizon. So that's the way it's always been for the Moon, but it's going to be true for the Earth on these long time scales of many millions of years, sorry, many billions of years. What's going to happen to the galaxy? Well, if we look at the center there, the Milky Way is surrounded by lots of small galaxies. This is a sort of map, if you like, of the local group that are gravitationally bound to each other. The Milky Way has lots of small galaxies around it, little satellite galaxies, as well as the familiar objects in the local group, M31, the Andromeda Galaxy, and M33, the Triangulum Galaxy. So we've already said that M31 and the Milky Way are going to collide. Essentially, all of the local group are going to end up in one big galaxy. Galaxies are cannibals. That's how galaxies evolve. That's how galaxies grow. They grow by merging with other galaxies, and generally speaking, large galaxies eat up smaller ones. So all of the local group is going to end up in one galaxy in the future. And when we think of the more distant galaxies, the ones we're sort of familiar with by looking at the Hubble Deep Field, we have to remind ourselves that the universe is expanding, and quite a lot of those galaxies in the universe are expanding and moving away from us faster than the speed of light. But that still doesn't mean we can't image them. So, for instance, a lockdown challenge I had in 2020 was to try and image, without a telescope, a quasar that's receding from us at twice the speed of light. It is possible to image objects receding faster than light. And when we look at the Hubble Deep Field here, we see lots of galaxies, some of which are receding from us at less than the speed of light, but quite a few of them are receding from us at more than the speed of light. That is not a limit on what we can see. And this particular image, most of what we can see there are galaxies. There's, I think, 2 stars in that picture within the Milky Way. Everything else is galaxies. But there will come a time on this extreme time scale of a trillion years or so when the universe will have expanded so much that it will not be possible to see these galaxies. In other words, the Hubble Space Telescope, if you were to do the same thing again in a trillion years' time, the same picture would look like that. You would see those 2 stars that are part of the Milky Way, but you would not see everything else in the observable universe because they would no longer be observable. In other words, the size of the observable universe essentially would change. And it's sobering to think that if a civilization comes to be in this sort of time period, if they lived in a galaxy and they built themselves a Hubble Space Telescope and they did a Hubble Deep Field, they would not see anything other than the stars in their own galaxy. They would not be aware of the fact that there were any galaxies in the universe other than the one in which they lived. So in that sense, we live in a very interesting time where it is possible to see all of these trillions of galaxies, providing we build the right sort of telescope. I said that it took 3 minutes to make a universe, roughly speaking. In 3 minutes, you can make all the hydrogen that the universe needs. But after a trillion years, after 10 to the 12 years, the hydrogen is starting to run out. There's a finite amount of hydrogen in any given volume that we're talking about, let's say, within the observable universe as we understand it at the moment. There's only so much hydrogen you can use to make stars, and it is running out. So new star formation is going to start slowing down. It's been thought that, well, if stars can't be made out of hydrogen, is it possible that you start making stars out of heavier elements, for instance? And some people have hypothesized that maybe it's possible to get nuclear reactions in stars not made of hydrogen, but made of heavier elements, and the heat from that core wouldn't necessarily make it to the surface, so the surface remains quite cool. So we know that some stars have got temperatures of thousands of Kelvin, like our sun or Betelgeuse, for instance, but maybe it's possible to have stars with surface temperatures of hundreds of Kelvin. So it's been hypothesized that maybe you can have nuclear reactions in stars in which there's ice in the atmosphere, frozen stars. And for Disney fans, frozen stars, I don't mean that on the left-hand side, okay? If that's the picture you've got, then just let it go, okay? So what we're actually dealing with is stars in which there might conceivably be ice, or at least the temperature of ice in the atmosphere, even though there are nuclear reactions going on in the core. Still rather hypothetical, but a very interesting idea. Before we can make any headway, we have to think what the universe is actually doing in terms of expansion. So let me just quickly remind you what we think is going on with the universe. If we think about the scale of the universe as a function of time, that's where we are now. So as of now, the relative size of the universe, let's just take it as 1 in terms of just a scale. So we can see that the universe used to be a lot smaller. But when did the Big Bang take place? Well, that depends on which of these colored lines you choose to follow. What are the colored lines? Well, the colored lines are lines that tell us about the evolution of the universe, assuming a certain amount of matter and energy exists within the universe. So you can't actually say the Big Bang definitively happened at a particular point. All you can say is, according to the model in which we have this much matter and this much energy, then that gives us a Big Bang that happened, let's say, 13.8 billion years ago. So for instance, if we thought that there's a huge amount of matter in the universe, then it would be possible that the expansion of the universe would be reversed and we'd have a big crunch in a few billion years. If there's a very large amount of matter, then gravity will be able to pull all of that back and it will expand for a little while, but then it'll end up as a big crunch, a so-called closed universe. But we don't think there's actually enough matter to do that. When we look into the universe, we don't see that much. If we saw, we don't have to worry about exactly what the numbers mean, but if we see less matter in the universe, then perhaps the expansion is going to increase effectively forever. As time goes on, this green line implies that the universe gets bigger and bigger and bigger and bigger as time goes forward. We actually think the best estimate of how much matter there is in the universe is given by the red curve. So not only is it continually increasing, it seems to be increasing in size at an ever-increasing rate. It looks like the expansion of the universe is accelerating, a so-called flat universe that's in an accelerating phase. So we're going to ignore the fact that there could in principle be a big crunch. Let's assume that the universe does continue expanding forever, which seems most likely according to our current methodology of looking at how the universe is behaving. And in order to make any progress, we can't keep going up by a factor of 10 each time, otherwise we'll be here all night. We're going to go up by a factor of 1,000,000. Each box is 1,000,000 times further into the future than the previous box. So 10 to the 30 is, I don't know what you call that. Is it a zillion years, a gazillion years? I don't know what the actual labels of these are. We're just going to look at the numbers and go up from 1,000,000,000,000 years upwards. So where did we leave it? Before we took this little detour to say the universe is expanding and apparently will expand forever, we said the hydrogen was running out. Okay, maybe some stars use other elements, but let's assume that once the hydrogen runs out, it's going to be very difficult to make new stars. Stars have finite lifetimes. They might last for billions of years. They might last for trillions of years, but star lifetimes are finite. So if we run out of hydrogen, what's going to happen? The age of starlight will come to an end. There will be a time when there are no more stars. The stars themselves will be there, but they won't be shining. In other words, there will be lumps of stuff still orbiting their galaxies, but no stars will be shining. There will be dead stars drifting like zombies around the galaxy. And the stars that we're left with are, for instance, white dwarfs, neutron stars, and black holes, the remnants of star explosions or the remnants of a star going through a red giant phase. White dwarfs sound like they're shining, but remember there's no nuclear reactions, they're just hot, and they will slowly cool off. Some of these stars are going to get thrown out of the galaxy. Quite a few of them are probably going to get thrown out of the galaxy. We know this happens occasionally because we sometimes see stars that are moving so fast, it's clear that they are exiting the galaxy at very high speed because of the interaction of different stars and how they swap energy and angular momentum. We think that's going to happen a lot in the future. Because there are no nuclear reactions going on in white dwarfs, they are basically just going to cool off. It's a little difficult to see what's going on there if we just make it a little bit brighter, but it's basically just a lump of carbon. That's effectively all it is. A lump of carbon that started off hot, but eventually it's going to cool down. So we're probably going to end up calling them black dwarfs. On timescales, look, we're getting really ridiculous here. We're now talking about millions of millions of millions of years into the future where these objects have cooled off. Any stars that haven't been ejected from the galaxy eventually are going to get gobbled up by the supermassive black hole at the center, we believe, of every galaxy. That might not be true, but at the moment the evidence is that essentially every galaxy has a supermassive black hole at the core. So some stars are going to be thrown out and the remaining stars are going to be eaten. So the galaxies are going to change quite dramatically. Work has been done to try and see what's going on in the vicinity of black holes, and an infrared telescope, this one in the back end of a jumbo jet called SOFIA, the Stratospheric Observatory for Infrared Astronomy, have mapped out infrared and mapped out the polarization of the infrared, which tells you what the magnetic field lines are doing. And it's thought that matter is streaming along those magnetic field lines and effectively is funneling matter into the supermassive black holes at the cores of galaxies. And we think that that will continue, and that will be the process by which supermassive black holes slowly eat everything else in the galaxy. But does it mean we'll ever end up with a universe that isn't made of atoms? Well, we know that atoms have got positively charged particles in the core called protons and negatively charged electrons going around them. And the positive nucleus keeps the electrons in position, if you like, in their place. But it's thought that protons might decay. We don't absolutely know. We've got limits on when that might happen. But if protons do decay, then basically atoms decay. Atoms fall apart. Now, we don't really know the time scale. I put this at 10 to the 36 as simply an estimate. It's probably not going to be before this, but it might be after this that atoms start to fall to pieces. In other words, the atoms we tend to think are eternal because the atoms in our body have been through a star and the star has gone supernova and the atoms have ended up on Earth, and then the whole cycle will keep going around multiple times, but not forever. We think that perhaps atoms will fall apart at the level of 10 to the 36 years or so. Even if that's not the case, even if protons don't decay and the atoms last forever, well, eventually even black dwarfs will evaporate through a process I'm not going to describe, but basically there will be no atoms left in the universe. Neutron stars aren't made of atoms, black holes are not made of atoms, so as soon as black dwarfs disappear, there are no atoms left in the universe. Not only no stars, but basically no atoms. It is thought that towards the end of their lives, any stars that do exist, which might be made, for instance, of carbon, like black dwarfs, it is thought that even they start to fuse into heavier elements. We are familiar with the idea that in the core of the sun, it's hot enough to fuse hydrogen into helium, or helium into carbon, or nitrogen, or oxygen. But how can that possibly happen if everything is so cold and everything has cooled off? Well, it's thought that fusion will still take place, but very, very, very slowly. In other words, it happens quite rapidly in the core of our sun because the sun is so hot. But it's thought that even in very cold objects like black dwarfs, perhaps the elements will start to fuse together into iron. That will be exceedingly slow, but given enough time, maybe that will happen. And again, we're talking about 10 to the power 42, 1 followed by 42 zeros of years into the future. So it might be pure speculation, but it might be that we end up with iron before we end up with no stars whatsoever. Galaxies collide in much the same way that I described earlier. Milky Way is going to collide with Andromeda. Essentially, all galaxies are going to be colliding with their neighbors, and the supermassive black hole in one galaxy is going to merge with the supermassive black hole of another galaxy, and that black hole will then get larger. So instead of having a supermassive black hole, which is millions of solar masses, or billions of solar masses, given enough time with enough galaxy collisions, you could end up with black holes with trillions of solar masses, effectively trillions of suns tied up in whatever is going on inside the middle of a black hole. But even black holes are not eternal. We're trying to get to eternity. We're almost there. Look where we've got to, 10 to the power 66. Black holes do not last forever, even though you think, well, black holes suck everything in and that's end game. Well, not quite. Black holes evaporate, it is thought. It hasn't been proved yet, but it's a very strong contender that black holes evaporate. Yes, you have to wait a ridiculously long time to see them evaporate, but it's thought that they do. So why do black holes evaporate? We have to borrow some understanding from quantum mechanics, not the largest things in the universe, but essentially the smallest structures in the universe. We believe that you can borrow energy from nothing. It might be how the universe came to be in the first place. You borrow energy from nothing, you make matter and antimatter, and then you pay back the loan of borrowing from nothing. You get some energy, you make a couple of particles, they annihilate with each other, and you put the energy back again. If that happens quietly enough, the universe doesn't notice. So it's possible to borrow from nothing, make stuff, and then put it back again. So you borrow energy, you make matter and antimatter, they then annihilate, and it puts the energy back again. That process, we think, is going on all the time. This is what the laws of quantum mechanics tell us about. How does that help us understand black holes? Well, Stephen Hawking said, what if this process goes on right next to a black hole? So if that represents the event horizon of a black hole, anything that crosses the line goes into the black hole and can never come out again. So what if you borrow some energy, make two particles, and whoops, one of them is lost into the black hole and the other one isn't? It looks like this black hole has emitted something because it's lost its other half. It can't annihilate with the other half because the other half has gone into the black hole. So there appears to be a net flux of something, whether it be photons or particles, from the event horizon of a black hole. This is what Hawking speculated about, and a lot of people believe he's right, and hence we think that in the far future, black holes will evaporate through this process, which is now called Hawking radiation. So what we would expect to see in a black hole is it would produce some radiation. As the black hole gets smaller and smaller, the radiation emitted gets larger and larger and larger. So you don't see much for a long, long time, but as the black hole starts to get smaller and smaller, the radiation gets stronger and stronger, and finally the black hole will disappear in a flash of radiation. Even the big ones will radiate. So the small ones radiate very rapidly, so that's why you don't find any small black holes around, because they've all evaporated already. And the really large black holes evaporate really, really slowly. But even the supermassive black holes lurking at the center of galaxies, even they eventually will evaporate. It will take trillions of times longer than the sort of black hole that you might make from a star, for instance, but they will eventually evaporate if you wait for this ridiculously long time. And we're now getting to the end of this second bar, and we've reached 10 to the power 84 years. Before we end, we have to say, where is eternity? Well, there isn't any limit to eternity. But if we get to 10 to the power 100, which is a Google, no, not that one, they spelt it wrong. They thought they were writing it as Google, but they spelt it wrong, and they've ended up with an LE rather than an OL. So a Google is 10 to the power 100. And it is said that after a Google years, that's it. That is endgame. There are no more black holes, and the black holes were the last things to go. So after a Google years, there is nothing left. Nothing happens. Nothing happens for the rest of eternity. And if that means nothing happens for the rest of time, then effectively time becomes meaningless, because how can you have a clock ticking time if nothing is actually happening? So in a sense, you can regard a Google years as being, well, that's pretty much it. If nothing happens from this point onwards, we can say that that is, if you like, the end of the universe. And just to remind you that 10 to the 100 is ridiculous, that is it written out in zeros. 1,000, 1,000,000, 1 billion, 1 trillion, a quadrillion, a septillion, yeah, okay. So you can see that 10 to the power 100 years, it's a bit of an illusion to have it on a scale like that. When you realize just how many years into the future we're talking, the only way that we can make sense of that is to talk about calculation of things that happen very slowly, and we think on that time scale the universe will be done and nothing interesting will happen from that point onwards. Trying to get your head round eternity is the same as getting your head round infinity. It just doesn't work. I think the best quote is probably from Woody Allen. Eternity is a very long time, especially towards the end. But the one I like that puts humankind in perspective in terms of the universe was born 13.8 billion years ago, and here we are now. Here we are doing our stuff, and we know roughly what's going to happen in the next few billion years or so. I thought this quote was quite a nice one. A human is a system for converting dust billions of years ago into dust billions of years from now via a roundabout process, which involves checking email a lot. So that's one way of keeping things in perspective when you're trying to get your head around what does a Google years actually mean. So let me finish, because I've had my time, with an epilogue. So far, I've told you how everything can come to an end, which is pretty depressing on the whole. So let's try and finish on an upbeat note. We live in what you might call a golden age. The sun is middle-aged. It's stable. It's well-behaved. It's billions of years old. It's got billions of years of life left in it. The moon is at just the right distance to stabilize the Earth's axis, to stabilize the seasons, and it gives us a spectacle of a total solar eclipse every now and again. Fantastic. Thanks to evolution, we are able to explore and discover and hopefully make sense of and understand the universe. And we can do that by visiting our closest neighbors and by building telescopes to allow us to see galaxies that are billions of light years away. And if we think of the past, humankind could not have existed in the very early universe because it needed generation upon generation of stars to fuse the light elements into the heavy elements. We needed stars to fuse hydrogen into helium, and then helium into carbon and nitrogen and oxygen and all the other elements that make us what we are. So we needed these early generation of stars to make effectively life possible for us. And we've just seen that if we look trillions of years into the future, the universe is looking dark and, let's face it, pretty damn boring. So we could argue the best time to exist is now. Thank you for listening.